Thanks very much, Oksana, for the kind introduction. It's nice to be back here. So I'm going to talk this morning about, I'm going to give an overview of the EPICS area detector package. I think many of you have probably heard a similar talk before, but probably not all of you. And I'm going to aim this talk today, at the Beamline scientist audience. So try not to talk too much about things that are, software jargon, and more of the things that I think would be useful to a Beamline scientist. So I'll go through what, sort of the goals, motivation for area detector, sort of an overview of the architecture, and then talk about a few of the drivers for detectors and cameras, and then spend probably more than half the time on these things called plugins that do real-time processing and file saving and so on for the images that you collect, and then talk also about the viewers and other clients for displaying the images or so on. Then we'll have a break. That'll probably take an hour, maybe a little bit more. We can have a quick break and then finish the morning with a demo where I go through and show in real time, both with a simulation detector and I've got a real camera here that we can do a demo with. And I'd like to keep this very informal, so if you've got questions, please just ask them anytime. So the goal of area detector is to have drivers for detectors that are popular at synchrotron beamlines. That was my motivation in running it. Of course, it's used in some other applications as well, including some cases in the machine, not just on the beamlines. It was designed from the start to have, high performance, and things are done efficiently. So we can handle detectors that go at 500 frames a second or even faster, and that the idea was to make sort of a basic set of parameters that are handled the same for all detectors, right? So that if you know how to use area detector on one camera or detector, it's fairly intuitive how to use it on another one. In fact, you might even be able to use the same script if you're only talking about the basic things like setting the exposure time, starting an acquisition, that sort of thing. Because that's a common set of actually EPICS process variables, you can develop generic clients that can be used with any detector. But we also wanted to make it easy to implement a new detector. There's basically just one C++ file to write. It's essentially EPICS independent. And then importantly, of course, to be able to implement the features that are specific to a particular detector, because every detector is different. It's got features you want to be able to take advantage of. So we didn't want just a least common denominator interface that could only do the things that every detector can do, which I would say that's kind of how the EPICS motor record is written, right? It's a least common denominator. You can only do the things with the EPICS motor record that you can do with virtually any motor. It doesn't really take advantage of the features of sophisticated controllers. And then finally, that we've got this middle level plug-in layer that adds capabilities like regions of interest, calculations, file saving, and so on. And the nice thing about having it as a middle layer there is that it is device independent. So once you understand how a plugin works, you understand how it works with any detector, not just the Perkin-Elmer, and so on. And these plugins run below the EPICS channel access layer or even below the EPICS database layer, so they have very high performance. Basically, you're just passing a pointer to these plugins. So I said we were going to avoid software jargon, sort of talking about the details of the software, but there are a few things that you need that it really helps to understand to understand how area detector works. And they're not really very complicated. I mean, the first is that the basic data structure is something called an ND array, which just means an n-dimensional array. So area detector was written so that it wasn't limited to 2 dimensions, although that's what an area detector sounds like, right? It was written to handle any number of dimensions. Right now, it's sort of hard-coded that it can only go up to 10 dimensions, which is probably plenty. But even on a 2-dimensional, camera like this, if it supports color, the data is 3-dimensional. And by supporting n dimensions, it lets the entire infrastructure for area detector be used for completely different kinds of devices. And you are using that here right now, because the Express 3 that some of the spectroscopy beamlines are using, or the XMAP, which is also a spectroscopy system, and the quad electrometers. There's Peter Siddons's quad electrometers, and some of you may be using the Kine ELS, Tetram, or AH501 series. All of those are using this ND array under the hood. And so that lets you use all the same plugins that you use for a 2-dimensional detector, we can use for these. So you can stream to HDF5 with one of the quad electrometer, for example, using the same software. Okay, so that's an ND array, and that's what basically the plugins that I'm going to talk about receive a callback every time there's a new image, which is a pointer to one of these things. Then there's a structure called an ND attribute, which is basically used for metadata. So every array can have a list of such attributes associated with it, and they stay with it all the way through the plugin pipeline. And these attributes can come from driver parameters, like the exposure time or the current frame number. But they can also, and this is probably the most common use, they can come from any EPICS PV or any user-written function. That's much less common. This is very common. So what this allows you to do is to store with every image these EPICS PVs. So you could store the positions of the critical motors on your beamline, or the Hutch temperature, or the ring current, or the gain on an amplifier, or any of the stuff you might want to know later that would tell you what were the experimental conditions when these files were collected. And these metadata will be written to the disk files if you're using the TIFF or NetCDF or HDF5 file plugins. Basically, I think the only plugin that doesn't support these attributes is the JPEG plugin, because I don't know how you put attributes in a JPEG file. And then finally, you don't really need to worry too much about this thing at the bottom, but there's a pool of these ND array objects so that every time the camera wants to get a new one, it doesn't have to allocate more memory, which could be megabytes, and then free it when it's done. It basically just gets one of these things from the pool, and when it's done, the memory already allocated goes back into this pool. And the plugins access these ND arrays in a read-only mode, because multiple plugins can be working on the same array at once. So you can't be modifying it. If the plugin needs to modify it, then it needs to make a copy. But if it doesn't need to modify it, there's no copying of the data going on, just a pointer. Yeah?
Are these ND attributes or structures, are they part of area detector uniquely, or they're independent of area detector?
No, they're part of the area detector package. Yeah. They're a data structure defined in area detector. Okay, so this is a diagram of the structure of it. I'll just go through it quickly. So somewhere down here you got your hardware. At some level above that, there's something you got from the detector vendor. It could be a library, a Windows DLL or a Linux shareable library. It could just be a socket protocol. This is how you talk to this detector. But there's something you get from the vendor. This is the area detector driver that needs to be written for a particular detector. And then above that is this layer of these plugins. So every time the driver gets a new ND array, it calls all the plugins that have registered to ask to be called on each new array. So that could be a plugin that does a region of interest calculation, or some image processing, or sending the data off to a waveform record so that a channel access client can display it, or saving it to a disk file. And these plugins are not only receiving arrays, some of them are also now a source of a new array. So a region of interest could, select some subset of your image and then pass that on to another plugin. So the file plugin could either be getting its data directly from the detector driver, so it's getting the whole image, or it could be getting its data from the region of interest, so it's just getting a subset of the image. And yeah. Then above that, this is just stuff that comes with ASIN in EPICS, databases, and then finally at the top layer, the channel access clients. So this could be CSS or MEDM or Python or ImageJ or Spec, or I guess it wouldn't be Spec here. But, okay, good. Blue Sky, that's Python. Yeah, so that's what the architecture looks like. And this should be enhanced, and I'm going to get into this. It's not just channel access clients now. There's this new layer thing called PV access, which I'm sure you've heard about, which was previously called EPICS v4, and there are now PV access clients that can get data out of Area Detector as well. So there are currently, I think, 33 detector drivers that cover a wide range of different kinds of detectors in Area Detector. These include a simulation driver, which I'll demonstrate later this morning, GIGI cameras, which I know a lot of you are using, the Prosilica AVT, Point Grey / FLIR also makes them. And then, in fact, any GIGI vision camera on Linux can be used via something called the Aravis library, which is a reverse engineered version of the GIGI vision standard. There are USB cameras from Point Grey. That's what this is. We've got the Pilatus and Eiger pixel array detectors from Detector, Princeton Instruments and photometrics detectors, and their spectrometers. Andor, CCD and CMOS cameras, PerkinElmer, Dexela flat panel detectors, web cameras, and Axis video servers, and then there are a lot more. Probably ones that are less commonly used, but I'm sure some of them are in use here. Any question? And remind me, I think I forgot just before, to repeat the question, because your voice may not show up there, so I'm probably going to forget. As I said, there's a standard set of parameters that every detector should implement, if at all possible, and like the exposure time and an acquire period, the number of images to collect, how to collect it, continuous. Collect multiple images and then stop, or just a single image. Obviously, to start and stop acquisition, setting the binning, a region of interest of the detector to read out, whether you should reverse the image in the flip it in the X or Y dimensions, and so on. So this is an example. This is a generic MEDM screen. It's called 80base.adl, and there's an equivalent CSS screen. And this screen can, in principle, be used to control any detector because it's only talking to those generic parameters that are in the base class. On the other hand, and this is a good, if you're writing a new detector driver, then this is a good thing to start with. But normally you wouldn't use this screen because this is probably exposing some parameters that your detector doesn't support, and there are some really critical parameters of your detector that you would like to, that you do need to support that wouldn't be able to be displayed on this generic screen. So this is an example of a detector-specific screen, in this case for the simulation detector, and it's got a few more controls on it that aren't on the generic screen. In particular, it's got effectively a button to pop up another screen which lets you control the details of how the simulation detector is working. And in this case here, you can see it's been set for 1024 by 1024 images, and it's got an int16 data type. So each of these images is 2 bytes, and it's running here at 485 frames a second. So the simulation detector can run very quickly, which is a good thing because it lets you test, the performance of plugins and how fast can you save files to disk and so on. Maybe before you get your real detector, is your infrastructure on your beamline set up well enough that you're going to be able to handle the data rate from your real detector when it arrives. So the simulation detector is useful. This works out to be about 1 gigabyte a second. If each one of those is a megapixel, so 2 megabytes times 500 frames a second. So that would saturate a 10 gigabit link. This is the more detailed screen on the simulation detector. So it's got 3 different modes. It's got a mode where it produces a linear ramp. It's got a mode where it produces an array of Gaussian peaks, and a mode where it produces a number of 2-dimensional sine waves. And it has independent gains for the x, y dimensions, and overall gain, and then gains for each of the individual red, green, and blue colors, which is useful for changing the color in a simulation detector. One of the things that I didn't say is that area detector, those ND arrays support 8 numeric data types. So signed and unsigned, 8, 16, 32-bit integers, 32, 64-bit float. And then it also supports color images. So, and in fact, of ones where the color goes in each pixel, red, green, blue, or each line, red, green, blue, or a plane, red, green, blue. So different ways of representing color images. So this linear ramp is just basically the x and y dimensions. The intensity in x and y is a linear ramp with an array index. And each time a new image is calculated, it just adds one value, a constant, to each pixel. This is very fast. So in this mode, you can run 1,000 frames a second. The peak mode shows an array of Gaussian peaks plus noise. It's slower, takes longer to calculate that. And the sine mode that's over here it gives you 2 sine waves in the x direction, 2 sine waves in the y direction. You can set the amplitude, frequency, and phase of each of those sine waves. And then you can control, is this sine wave and this sine wave added together or multiplied? So one can be modulating the other. So you can get fairly sophisticated images out of it. It was useful, I wrote it in part to be able to test an FFT plugin, because in this case, I know what frequencies I'm putting in, and I better get the same frequencies out, right? And amplitudes. So this is just a picture of what the linear ramp mode looks like in color mode, where the gains of the red, green, and blue have been set to be different. If they're all the same, it'll be black and white. The gains of red, green, and blue are all the same, it'll be black and white. But if you set them to different values, you get this spectrum of colors. And the x and y gains control basically the tilt of these lines, right? If the gain in X is 0, they'll be vertical. If gain in Y is vertical, is 0, they'll be horizontal. This is using the Gaussian peak mode, where I've made a lot of peaks in both X and Y. You could make just one big Gaussian peak here, but I made a large array, and then this is the FFT plugin running on that, right? So this is basically the diffraction pattern of this. And this is what the SIM detector looks like in the sine wave mode, either in black and white or in color. So you can see there's a low frequency sine wave in X here, and a high frequency one, and the same in the vertical direction. Okay, so let's get into some real detectors, not just the simulation detector. So this is a screenshot of a real detector for the Pilatus. You see it looks quite different from the base one, the 80 base or the SIM detector, because the Pilatus has a lot of features that are different, that are not in the base class, including things like, the threshold energy, the actual beam energy that's important to specify for flat field normalization that is done in the Dectris CAM server software. What value you fill the gaps between the modules with, some environmental information on the temperature and humidity in the detector. And then, this is an example of a detector where the vendor doesn't provide an API to let you get the data. Now, there's CAM server, which is their software that drives the detector, does not provide a way to send data to a client. The only thing it knows how to do is write a file. So CAM server is saving these files, and area detector has to read those files in order to get the data back into area detector so it can pass it to the plugins and so on. See if there's anything else I want to point out here. Yeah. The flipping of the images would have to be done in a plugin called a transform plugin. I mean, if the vendor supported flipping, which like Point Grey does, then you can do it in the vendor library. But the Pilatus CAM server doesn't support flipping images, so that you would have to put a transform record into the processing pipeline, either before you see the images, if you only need to flip them for the operator, or if you want them flipped in the final data file that you're writing. They won't be flipped in this file, but if we can read this file, flip them, and then write another file, either a TIFF file or an HDF5 file or whatever, and there they could be in the correct orientation. I did want to point out that there's these sort of standard blocks here. Like this one is a block that has all this information about sort of the setup of the detector, and every detector and every plugin has a name for that. It's called the ASIN port. And you do need to know what that is, because if you want to change your file plugin from getting data directly from the detector to getting it from a plugin, it's this string that you type in to say, where do you get your data? You either get it, in this case, from PIL, P-I-L, which is the detector driver, or you might get it from ROI1 or Trans1 for the transform plugin. And then there's information on here about what version of area detector you're using, what version of the driver you're using, what version of the vendor library you're using. I put these things in because then when people complain and say it's not working, I can at least say, send me a screenshot here and I can tell you what, is it a problem that's already been fixed? Then this is a standard block that appears in all detectors. In other words, this almost never gets changed. So we just use this graphic element here because that calls up the various different plugins. But this is probably, this block here is not standard. it's because it's got stuff that's specific to the Pilatus detector in this case, and these are completely new. But this attributes, which I'm going to explain in a little while, is standard, and so is this shutter one. So you'll see every detector screen has a block that looks like this, has a block that looks like this, and this, and so on. Yeah?
I have a very generic question. What happens if you put your acquire period shorter than your exposure?
That depends on the particular driver and how it's implemented, but basically it would be ignored, right? You know, so in general, it would be ignored. In some vendor libraries support the concept of an acquire period. You know, so you tell the camera how fast it should run, and then as you say, that would always have to be at least a little bit longer than the exposure time. For vendor libraries that don't support the acquire period, the area detector driver will simulate it. So it'll take a picture, figure out how long that actually took, and sleep for that time minus the period, you know, and then do it again. But if that sleep comes out to be negative, it just does it again immediately. Yeah.
I got a question about the delay open time. So would it support a negative time or it's always positive time? So what would that specifically mean?
That's basically telling it how long does it take. Oh, sorry. Yeah. The question is, what's the meaning of the delay, open, and close on the shutter here? And basically, it has to do with like how long you put in the number of how long does it take the shutter to actually open after you tell it to, and how long does it take it to actually close after you tell it to. And a lot of times it's only the difference between those two numbers that matters, right? You know, let's say you're telling it to open and then you're sleeping for 3 seconds because that's the exposure time, and then you tell it to close. How long you sleep or how long you wait after you tell the shutter to open before you start the detector would be controlled by those numbers. Yeah, and there's a control here that says where do you get, you know, what type of shutter am I using? And there is, the choice is usually that you can do it with an EPICS PV, at which point it's done in software in the driver, right? It tells that EPICS PV to change state, then tells the detector to take an image, and then puts the PV back into the other state. But many vendors also support a shutter. So there's a choice here. If this detector does support shutters, which in the case of the Pilatus, it doesn't. The Pilatus cam server doesn't understand shutters. So, you know, then the only choice would be an EPICS PV. So this is just an example. This is a driver for a program called Lightfield, which comes from Princeton Instruments. It's actually quite a nice graphical program for controlling the Princeton, not only the detectors themselves, but also the spectrometer. You know, if it comes with an Acton spectrometer, and this is controlling the gating of an image intensifier. So this is quite a nice user interface. So in this case, what we did is just the area detector driver, this application exports its functionality as an object and in Windows. And so the area detector driver basically is just automating this application. So the user sees the same interface they would use if they weren't using EPICS, or they can control it from an EPICS screen. But when they change, this is like the image intensifier gate width. All the controls here are basically just driving that light field application. So that's just another example of a way an area detector driver can work. This is yet another one. This is called a URL driver. So this is a driver that can read images from any URL. So it could be used to read an image from a file, right? And into area detector, or it can read from a website. And this for instance, is an Axis video server that we have running in a station. And every time a new image comes in, it refreshes this file called hugesize.jpg. Right? So all I'm doing is periodically reading that file, and now I'm seeing the images on that web camera, on that Axis video server, which is effectively a web camera. And this driver uses a package called Graphics Magic to actually read the images, and Graphics Magic knows how to read a whole bunch of different image formats. So it knows how to read JPEG and TIFF and PNG and a bunch of file formats. So, and all you do is put, it gets that from the file extension. So if you put JPG, it's going to look for a JPEG file. If you put TIFF, it's going to look for a TIFF file. This is the Perkin-Elmer flat panel detector driver. It's, I think you guys have probably used this. Again, it's got some things that are specific because this is one of these detectors. The background drifts a lot, so you want to periodically measure a flat field image, or not a flat field, but a dark image, with the shutter closed. And then it subtracts that from all the frames that you're collecting, and that's done in the vendor's FPGA. So you tell it, I want to collect 10 of these frames with the better close the shutter first, and then it'll and then acquire offset correction. You can do the same thing with the gain, which really means flat field, but that's hard to do, right? We have a hard time making flat fields at a synchrotron. So typically people don't do this, just using the vendor flat field file if there is one. You got a bad pixel file. Yeah. I'm going to talk about a few drivers for these cameras from a company called Point Grey, because I don't think they're widely used here yet, but they do have a lot of nice features. So they sell gig E, USB 3, and now 10 gig E cameras. And these are pretty high performance, low cost. This camera is one of them, this USB 3 camera here that I'm going to use today in the demo part. They recently released a new series of cameras, including these 10 gigabit. They call them Oryx is the model name. And that uses a different SDK, software development kit, than the one that the existing Point Grey driver used. So I recently wrote another driver called, and that new SDK is called Spinnaker. So I wrote an AD Spinnaker driver that can handle not only their new cameras, but it works with most of their old cameras as well. Anything that uses either gig E vision or USB vision. So here's a couple of models, 3 different models. So this is a 1 gigabit, a USB 3, and a 10 gigabit. And you see the resolution. Well, they have a whole bunch of different resolutions. This is just an example of one that's 1280 by 1024 pixels, 83 frames a second, and it's $325. And that's going at like 1 megabyte a second. USB 3 camera is $1,000. It does like 160 frames a second, which is 350 megabytes a second or something. And then finally, this new 10 gig one is like a 2.5 by 2K camera that does 163 frames a second. It's only $1,800, and that works out to be almost 800 megabytes a second. So this is one of the inexpensive 1 gig E cameras. This one happens to be about $500, and this is about 5 times cheaper than the Prosilica cameras that we were getting in the past with comparable performance. And this one happens to be power over Ethernet. So you don't need a separate power supply, but you do need a power over Ethernet switch. This is the one I'm going to be demoing today. So this one is, it's an amazing chip. It's this Sony IMX174 chip. It's got a very high quantum efficiency. It's only got 7 electron read noise, 8 or 12-bit data, does 162 frames a second, which works out to be about 356 megabytes a second. That's about 3 times faster than gig E. Like I say, USB 3 interface. And this is the camera that's now in use for doing tomography at least 3 of the APS beam lines. and it replaced things like the Andor Neo and the PCO Edge for something like 15 times less money. And then finally, this is the new 10 gigabit Ethernet camera. This is another Sony chip, and it's got 2.2 electron read noise for an uncooled camera. That's pretty amazing. Again, 8 or 12-bit data. This will also do 162 frames a second, but because it's a lot more pixels, that works out to be almost 800 megabytes a second. And again, it's very reasonably priced. And in this 10 gig, these are the models they have. So they go from like 4K by 3K, 4K by 2K, 2.5 by 2K for range of prices here. And then the frame rate, all the data rates are basically the same. So the higher resolution ones are fewer frames a second. This is just a screenshot of the Point Grey driver. You've got controls now for fairly sophisticated triggering. Strobe means it can put an output, a TTL output that could trigger something on your experiment. And then there's controls of. They have a nice interface with being able to say for every feature. Like the shutter, which is the exposure time, in the current mode, it will give you the information on what's the min and max. So you can make a slider here that is in EPICS that only goes from the min and the max, and you know what the min and the max are. Their SDK is pretty good that way. Okay, I'm going to move on to. Let me just see how I'm doing for time here. Move on to plugins. So plugins are designed to do this real-time processing of the data. They run in the EPICS IOC. As I said, they receive their data from callbacks from the drivers or other plugins. And an important thing is that they can execute in their own threads. That's called non-blocking mode. Or they can execute in the callback thread. That's called blocking mode. So if it's in the non-blocking mode, then there's a queue. And every time the driver has a new array that the plugin should process, it just puts it in a queue. And the driver immediately returns, right? It doesn't have to wait. It just has to put the thing in the queue and come back. And which is nice because it doesn't slow down the driver. If it executes in the callback thread, in other words, that it's in the blocking mode, then the driver that did the callback to the plugin actually executes the code of the plugin and before it returns. So there's no queuing, but obviously that slows down the driver. But there may be times when you want to do that before the detector says it's done with a frame, you want to be sure that the statistics plugin has run. Because let's say you're doing a step scan, and you trigger the detector, and then one of your detectors that you're counting is the counts in a region of from the statistics plugin. You want the total counts in a region of interest. You want to be sure that that total count number has updated before the detector says that it's done. Otherwise, if you're not, and that's running in a queue, you could be getting stale data because the plugin is falling behind the detector driver. So there are times you want to switch it to blocking, but most of the time you want it non-blocking. All plugins now allow enabling and disabling the plugin, throttling the rate. So you could say, I only want this plugin, I don't want it to process on every time there's a new image, only once every half a second or 10 times a second. And then you can, in real time, you can change where does that plugin get its data. Does it get it from the driver? Does it get it from another plugin? And as I said, plugins can be sources of new ND arrays as well as consumers of ND arrays. So you can build up a processing pipeline that runs at very high speed because each of these plugins is running in a different thread, and on a machine with multiple cores, they're each running in their own core.
Mark,
Yeah.
So this blocking and non-blocking plugins, does it work from plugins to plugins also?
Yes. And so basically, it does, the plugin doesn't know who called it. Was it a driver or was it another plugin, right? And it just controls how does when the callback occurs, what happens? Does it execute the code? That's blocking. Or does it just put the array in a queue? That's non-blocking. So yes, it's transparent.
And how do we set that?
Okay, good question. Oh, well, I think you got Sanjit's question because he was close to the mic. Sorry, I didn't repeat it. Okay, good question. So you set it here. So every plugin screen that you see will contain this subset of, like sub-display, right? This is included in all the plugins. If you press the More button here, you'll pull up a bigger list. So and this is all the stuff that is independent of what plugin it is, right? This is the stuff that in object-oriented programming terms comes from the base class. All plugins have all of these PVs, and they work in all plugins. Then there's additional ones that are specific to the statistics plugin or whatever. So this is the port. So again, that's the thing you need to know if you want to tell another plugin where to get its data from this plugin. That's the string you need to look for. This is just some information. What kind of a plugin is this and what version is it? This is where you would type a new string to say, instead of getting my data from port sim1, get it from ROI1. Occasionally, you need to say something other than address 0, but it's almost always address 0, so we'll ignore that. Answering Sanjit's question, this is where you enable or disable this plugin. And when you take Area Detector out of the box, all the plugins are disabled, right? So if you don't have an auto save file, these will all be disabled. So you've got to enable the plugins that you want to enable. This is the minimum time. If it's 0, then there is no minimum time, and the plugin will process every time it gets a callback. But if you put 0.1, the units here are seconds, so if you put 0.1 here, then even if it's getting arrays callbacks at 100 hertz, it'll only process at 10 hertz. You've slowed it down. This is where, to answer Sanjit's question, you say callbacks block yes or no. So no means you're queuing, you're not blocking. This is just how many times has this plugin processed, and you can reset it to 0. This is how fast is it currently processing. It's doing 250 images a second. It tells you here, every time the plugin executes, it measures the time of day when it started and the time of day as it exited, and tells you the difference. So this is how many milliseconds it took this plugin to execute. And that can be useful to see, okay, if this is taking essentially 10 milliseconds, you know this plugin can only do about 100 hertz. If you try to go faster, it's going to start to, it's going to fall, it's not going to be able to keep up. This is how many arrays have been dropped, and I haven't mentioned that. But now if you're queuing into a queue and they're coming in faster than the plugin can process them, eventually the queue is going to fill up. And then it's not going to be able to process the next one because the queue is full. And these queues are holding images, right? So if it's buffering 1,000 images in the queue, that could be gigabytes of memory. So you can't set it to infinite because your computer will fall over. It won't be able to keep up. So, yeah, Sanjay.
Follow-up question. It applies to TIFF also. So does it wait for TIFF to write in the disk, or it's only the writing to the TIFF? How does it work? Because if we are writing the TIFF files from the plugin, then it's saving in the disk.
Yeah.
Is it going to wait for the disk?
No, there's a certain rate at which the TIFF plugin can write to the disk, right? That will be reflected in this time. How long, because this time includes the time to actually, for the TIFF plugin to write to the disk. So let's say it can write 100 frames per second to the disk. So this is around 10 milliseconds. Then if you get them faster than that, it's not going to be able to keep up. Does that answer your question?
No, because so it's writing the TIFF is for Perkinel now.
Yeah.
In particular, we don't have any buffer, so we are writing on the disk.
Yeah.
Is it going to wait for the signal from the disk, that whether it is written or not?
No, first of all, I mean, the Perkin-Elmer driver doesn't write TIFF files. You're using the TIFF plugin, right? And I realize this is not a current screenshot. So there's one thing here, which is queue size, free and available, and this doesn't just exist on the more screen. That's also on this screen. This must have been taken some time ago. So this is where, for all the plugins, you can control at runtime how many elements are in the queue. How big is this buffer? So right now, you see it's set to 200. So the queue has got 200 elements, so it can buffer 200 frames. But the number of free elements right now is 0, and which means it's not keeping up. Right? When you first turn it on, let's say this was running at, let's say the detector was running at 200 hertz, and the TIFF writing plugin could only write 100 hertz. You would see the number of free elements in the queue start out at 200 and then go down by 100 a second, right? So if it was, so it would take 2 seconds. In 2 seconds, because you're falling behind by 1 frame, by 100 frames a second. You can write 100, but you're getting 200. So this would have gone to 0 in 2 seconds. But let's say that you're doing an experiment that's a finite number of frames, right? You're rotating your sample, and you want to collect 2,000 frames as you rotate 180 degrees. If you've got enough memory, you can just set that queue size to 2,000. And now you quickly rotate your sample. The detector collects all 2,000 frames, but they're not being written to disk fast enough, but it's just filling up that queue. And now at the end of the experiment, you just have to wait for the TIFF writer to finish, right? And that's a very common thing to do. You just have to, you have to make sure that your computer has enough memory to buffer all the images you want to collect in one experiment, or at least as the number by which it's going to fall behind, because in this case, in the hypothetical case I was just talking about, it can write half the speed. So, you would have had to buffer 1,000 frames, not 2,000 frames. And when you type 2,000 here, it doesn't actually allocate that memory. It only allocates it if it's needed, if the queue starts to fill up. So even if you think you only need 1,000, as long as you have enough memory for 2,000, type 2,000 to be safe. Okay, so let's pretend that was over here because it really is. So the number of dropped arrays is how many times did the driver call back, try to put an image in the queue, and the queue was full, and then at which point it just drops it. Right? There's nothing it can do. So this is how many times was the queue full. And you can reset that to 0 if you're doing some tests as well. And then this is information on the last ND array that this plugin received. How many dimensions was it? What was the array size? What was the data type? What was the color mode? Every ND array has something called a unique ID, which is a unique integer that typically starts at 0 and just increments, that uniquely identifies that image. So let's say your driver was dropping some frames and you only got 1,800 TIFF files instead of 2,000. In each TIFF file, it tells you the unique ID. So you can tell which frames were dropped, right? You know which unique ID was dropped. Similarly, every ND array has a timestamp field associated with it, which is the time in seconds since January 1st, 1970. January 1st, no, 1990, because this is an EPICS timestamp. It's not a POSIX timestamp. And EPICS, because there was no EPICS before 1990, they made it start in 1990 because it bought them another 20 years before it was going to run out. Anyway, so this is a double precision number. It's good to about a microsecond today. Right? It won't be quite as good 20 years from now. It's good to about a microsecond. So there's a timestamp there too. That tells you what time that frame was collected. And we're going to get into what these attribute files are. Okay, so that's the screen that presents you a lot of the information. Over here, there's some additional stuff. Let me see. Well, there's the number of, a lot of it has to do with you can take each plugin and say, instead of that plugin just running in one thread, you can create 5 threads for that plugin. Yeah?
I just had a quick question about the dropped arrays that you had there.
Yeah.
Is there a way to set whether it drops the one that's currently collected or can you kick the oldest one out of it?
Right now, it always drops the current one. It doesn't kick the old one out. So you can have a plugin running, you can have multiple threads, and I'm going to have another slide on that. And all this stuff has to do with if you're running multiple threads. And again, if you're, yeah, forget that. There's a more screen here that has some additional things that are less commonly used, and you probably won't use them very much. But we'll go through them in the demo. Okay, so there are currently 20 different plugins that perform a wide variety of operations. The standard arrays plugin takes arrays and basically puts them into EPICS waveform records so that you can access them with channel access. There's an ND plugin PVA that does the same thing, but it converts them into EPICS v4 or PV access NT-ND arrays. And exports those over PV access with an internal PV access server. So this can be used to send structured data to PV access clients. And I'll get into this later. Our region of interest plugin selects a subregion of the detector, and it can optionally bin it, reverse it in either direction, and convert the data type. It can divide the array by a scale factor. So let's say you're binning 3 by 3. What that really does is just add up 9 pixels to make the new value. But that could lead to integer overflow, right? Because if you had 8-bit data and you add 9 of those values together, it could well be bigger than 255. So this allows you to scale it so that the output would still fit within the data type that you want. Or you can promote the data type and add 9 pixels together and make it into a 16-bit integer instead of an 8-bit integer. The transform plugin does what you were asking about, rotate or flip an image, 8 different operations. Statistics plugin computes whole bunches of different kinds of statistics, basic statistics, centroid statistics, profiles through the image in the X and Y directions, and a histogram of the image. And each of those can be turned on and off separately. There's something called a region of interest stat plugin. So that combines the features of the region of interest plugin and the statistics plugin to let you have, but it lets you have multiple regions of interest with simple statistics. So instead of, let's say you got a one-dimensional detector and you want to have regions of interest around each of your fluorescence peaks. You don't want to have 32 statistics plugins and 32 regions of interest plugins, just when one plugin would do. So that's what this does. But it's simpler statistics than this one.
So now we have 4 RIs only. So does it mean that in the new version we will have more?
Let me get into that. So the question was, there's only 4 regions of interest. The number and which plugins are loaded in your IOC is just determined by this little script called commonplugins.cmd, right? And that loads 4 region of interest plugins. But there's nothing to prevent you from loading more region of interest plugins. or fewer. And similarly, it has 5 statistics plugins. And I set that up so that each of those statistics plugins, the first 4 would be getting their data from the 4 regions of interest, and the 5th one is set up to get it from the whole detector. But that's reconfigurable at runtime too. So it's just, that was a decision that was made. You would also have to change your screens, right? Because right now the related displays only call up 4 regions of interest, not 6. But you write your own screen and then there's no limit. Okay, so there's a processing plugin that does a whole variety of arithmetic processing on arrays, like background subtraction, flat field normalization, offset and scale, high and low clipping. The most powerful thing is it does this recursive filtering in the time domain, so it can sum 10 images, or it can average 10 images. It can show you the difference between image n and image n plus 1. So you can see just what's changing in the image. And again, convert to a different data type. There's an overlay plugin that lets you put graphic overlays on an image, so you can graphically see where your regions of interest are. You could, you can put a cursor where the X-ray beam is, and the user can see where the X-ray beam is. And not doing that on the client, but doing it on the server, so no matter what client they're using, they see where the beam is. It has some simple text display as well. There's an FFmpeg server plugin, so that converts the images into an FFmpeg stream, and you can now view them in any web browser. That's used a lot at Diamond. I haven't used it. It only runs on Linux, but you guys are using Linux. But it wouldn't run on an IOC that runs on Windows. And then there's some less commonly used plugins. One that lets you extract attributes from arrays, one that buffers all your arrays into a circular buffer. It's kind of like a triggered scope, right? So it's storing your arrays in a circular buffer, and then when some trigger condition is met, and it could be a manual trigger, it sends out some number of pre-trigger images and some number of post-trigger images. But the triggering can be done on the values of attributes. So you could run your array through the statistics plugin, and whenever the maximum value in the array exceeds 10,000, trigger it, because there's some glitch happening on your beamline, that only happens once a week. And this would let you capture what do the images look like just before and after that glitch. There's a time series plugin that's more useful for one-dimensional data. Fourier transform plugin that works either in 1D or 2D waveforms. A color conversion plugin. These are things that are less commonly used. Okay, so this comes back to the question about the 4 regions of interest. So this is a screen called commonplugins.cmd. So it shows you at a glance all of the plugins that are defined in that common script file that I just mentioned. So it loads one of these standard arrays plugins, one of the, this is an old screenshot, so there's now a PV access plugin right here, a processing plugin, one transform plugin, a couple of color converts, an overlay, but each overlay plugin can do any number of overlays. So, it isn't limited to one rectangle. It could do 10 rectangles and 4 ellipses. You can have a whole bunch of overlays and turn them off and on individually. 4 region of interest plugins, 5 statistics plugins, and then plugins for the NetCDF, TIFF, JPEG, Nexus, Graphics Magic, and HDF5 file plugins. Yeah?
Can you say something briefly about when it's appropriate, when we'll be expecting to use PV access or not?
Yeah, that's a really good question. So the question is, when would you use PV access compared to channel access? I think for accessing the arrays, for the images from area detector, people should switch to PV access as soon as possible. First of all, it's ready for prime time, because my understanding is that there is a widget in CSS that displays PV access. There's an ImageJ plugin for ImageJ that does PV access. and there's all the standard utilities like PV. There's PV-get, which is the equivalent of CA-get. But you might not have PV access in your favorite language yet. Like Python. I don't know if the Python distribution you guys are using has PV access yet. Does it?
Not yet.
I think that might be true. But there is a Python PV access library. Unfortunately, there are two. They're sort of duking it out. But Michael David Saver has written one, and then the one that's in the main V4 base development tree is another. But they'll settle on one or the other fairly soon. And I'm going to mention, I do have a slide where I'll talk about the advantages of using PV access compared to channel access. So this is a region of interest plugin. I got to go quickly here. So this is the stuff, the standard stuff you've already seen. On the left-hand side of each of these displays is the standard stuff for every plugin. So this is the stuff that's unique to this plugin. So you can tell it, for each dimension, X, Y. The region of interest plugin will work in n dimensions, but I've only set up the screen to work in 3 dimensions. So you can set for each dimension a binning, where the region of interest starts, the region of interest size. Do you reverse the pixels in those dimensions? Is the data type automatic? Means the output data type is the same as the input data type, but you can also select here all the data types. So you could switch it from whatever. This is coming in as int 8. You could change it to int 16. You can enable or disable scaling, and this is the scale divisor if you enable scaling. Questions? Okay, this is the statistics plugin. Again, the common stuff on the left. So it's computing here basic statistics, which is minimum, maximum, the X and Y position of the minimum and maximum, the total number of counts, the net number of counts, the mean and sigma, and the net counts is the total counts minus the counts per pixel that are determined by drawing a boundary around the image that's this number of pixels wide, computing the average counts in that bounding box, and then using that number of counts per pixel to subtract from everything, all the pixels in the image, which is equivalent to drawing, to fitting a best fit plane to that boundary and subtracting the counts. So that's the net. Then you can enable a centroid calculation. So, and it has a threshold. So you can say, let's say you've got a beam, the image of a focused beam on your sample, on a scintillator or something. But there is some background intensity, and you don't want that to contribute to the centroid calculation. You just want to count the beam. So if you say, oh, that background is like 50 counts, but the in beam is 220 counts. So you can set a threshold of 60 counts, and only stuff above that contributes to the centroid calculation. So you're just seeing the beam. So it tells you the X and Y, sigma X, sigma Y, and sigma XY. This again is an old slide. This has been enhanced to have some ellipticity information. It tells you is the beam horizontal or vertical or some orientation in between. It also has skewness and kurtosis and some higher order statistics there. It's got a thing called time series, so you can collect any of these statistics as a function of time and buffer it in this plugin. And that's very useful. Like, let's say you're collecting 500 images a second as you do a scan, and you'd like to see where is the minimum as you scan a wire through the beam. You're probably not going to be able to write a client that can grab those values fast enough, and be sure you're not going to miss some. But here, if you just do a time series and you capture 2048 points and you start it, then you're guaranteed not to drop anything. And when the scan is over, you just read out a one-dimensional array here, and you have, you know, that profile. So it's a good way to do data acquisition of statistics efficiently and without having to try to keep up in whatever client you're using. This lets you enable profiles in the X and Y direction, including like the average X profile and Y profile. Also, you have what I call cursor X and Y. So basically, you can move a slider here and change where is the profile you're measuring in X and Y. And then finally, you have a histogram you can enable, and you can say, you know, what's the minimum, maximum values of the histogram you're interested in, and the size of the histogram. How many bins in the histogram?
One quick question. So for the statistics, the middle top screen, if you don't want to subtract any background, you set that to 0?
Yes, repeat the question. So the question is, if you don't want to subtract any background, can you set this to 0? I'm not sure, but you would just ignore the net, right? Because the total count it would be this number and this number would be the same if that was 0. So just don't use the net counts, use the total counts if you don't want to do background subtraction. So this is examples of there's a histogram of the image. That's the cursor Y, the average X. These are time series now. So this is time versus intensity. For what was this? The centroid. This is the total counts, and this was the centroid in the Y direction. This is the overlay plugin. So this is showing 3 different overlays, a couple of rectangles and a cross. And one of the things that you can do is configure it so that the overlays get their value. The overlay position or size gets its value from some channel access PV. So for example, from the statistics plugin. So you could, if this laser pointer here, that's what this bright spot is if you've set the statistics plugin to measure the centroid of that by masking out this background or setting the threshold above the level of this background, then you could make the position of this crosshair get its value from the X and Y centroid. So as you move the cursor, this cross will track it with a little bit of a lag.
So question on this, the thickness of the lines,
Yeah.
and these overlays. We are starting to use very large cameras on the screen, and then we go
Yeah.
downsize, and then the lines vanish. Is there a place where we can change the
Yes.
thickness of these lines in the overlays?
Yeah.
It could be done during the demo later. Maybe.
Yeah. Wait, where was I just? This, again, this screenshot is old. There is now a line thickness. So you can set the thickness of the line. We saw exactly that, right? Because when image J, for instance, interpolates an image and downsizing it, it can lose the line. So yes, you can set the thickness of the line. This is a processing plugin. So you can do background subtraction, flat field normalization, scale and offset, high and low clipping. And then this is the recursive filter. So you could say, in this case, you know, it's set for filtering 100, using 100 images as the filter size. And in this case, the filter type was a recursive average. And then there's some preset filter types, but there's a bunch of filter coefficients, and we're not going to go through this, but you can basically create your own filter just by changing these coefficients. It's effectively the sum of the previous filtered image and the new image, and you can adjust those coefficients so that you know, it's the difference of the two images or an average or whatever. Yeah.
So question is this one. So in some applications, like in the phase applications, it's not the background that is subtracted, but it's some kind of a intensity image, and then as the images are collected, people are looking for the difference between some kind of a typical image, you know,
Yeah.
You know, because there's a
huge diffraction peak, but they're looking at the stuff that is weak.
Okay.
The Prac plugin would be probably the right place. But
Yeah, I'm embarrassed. A lot of these are old screenshots. Well, they're not that old, but they're new features here. So there's now the ability here and here to read a TIFF file. Instead of what you had to do here was, during your data collection, you were measuring a background and you said save. And now that became your background image. But that's kind of limiting because it means you have to somehow put your experiment back into the configuration where you can actually collect a background, which, move your sample out or close the shutter or something. And sometimes you might want to measure that once and use it for days, right? And so now there's the ability to read a TIFF file. If your diffraction image, the thing you're trying to subtract, is saved as a TIFF file, you can now just read it in and it'll be subtracted. And it doesn't have to be something you even collected. It could be something you calculated, right? And the same for the flat field normalization here. Yeah?
Two questions. For the processing, post-processing that's being done, what's being saved out in the way of provenance about what post-processing was done to produce that image?
That's a good question. So every driver and every plugin has a field here called an attributes file. So I told you that you could have attributes associated with every image that are the metadata, right? And those can be added, those attributes can be added anywhere along the processing pipeline. And what you enter here in this field is the name of an XML file that defines, it's basically just a list of the attributes that you would like this plugin to add, where they get, and give them a name and a description, and where do they get their value. So for this plugin, you could create such an XML file that has the values of all these PVs. So now, if you then send that to your disk file plugin, it will store, you will know all of these settings for every image that was processed by this plugin. Okay? And the same thing with the statistics plugin. The statistics plugin, this plugin is intended to be something that is part of a pipeline, right? It sends its output somewhere because it's modifying the image. You wouldn't think of the statistics plugin as being that type of a plugin, right? All it's really doing is producing numbers, right? So you wouldn't think of the statistics plugin as feeding into further downstream plugins, but it can. And the reason you would do that is you might want every image that the statistics plugin processed to tag onto it, what was the minimum and the maximum and so on. That can be useful for that triggering application I talked about with the circular buffer. So, the statistics plugin finds the min and the max, and then that's used as a trigger for the circular buffer plugin. It's a rather obscure application. People aren't using that a lot, but you can do it. Does that answer your question?
Yeah.
Yep. Okay. Okay, so this is just an example of the statistics plugin where the processing plugin where the images have a 30 microsecond exposure time. So they're very noisy. In fact, there are only 5 non-zero, I think, intensities. So it's either 0, 1, 2, 3, 4 in this image. So it's very spotty. This is what the histogram looks like when it's expanded out. These would all be collapsed down at 5, but I've multiplied the intensity by 50 or something. And then this is a n equals 100 recursive average on that. So when I average 100 images, it takes that very noisy stuff, makes it a much smoother grayscale, and the histogram has all been filled in. Yeah?
Obviously, when you have a recursive filter, you add some latency to the output compared to the unfiltered
Correct.
trace. Is there a relationship to blocking versus non-blocking, whether or not you have a guaranteed latency?
There is no guaranteed latency. Well, I mean, it's predictable in the sense that if you're averaging 100, you're not going to. And I should have pointed out that on here, that this plugin can do callbacks in two situations. And right now it's selected to do a callback on every time it processes, so you would watch the average improve, right, grow. Or you can say only callback on every nth time that this plugin processes, so that you would only get the final result. The final result is going to happen only once every 100 frames, right? So it's going to be a hundredth of the frequency and a latency that's 100 frame periods. But when the queue is filling up over here, there's an additional latency that's non-deterministic, right? It depends on how fast the CPU is. And you can see that if you're looking at an image and you move your camera, the thing you see on the screen doesn't keep up if there's a lot of latency in the pipeline. Yeah.
Can this be split between multiple servers? If, for example, one server doesn't have enough capability
Yep.
to process all this, can't we just run certain plugins on another server and take advantage of it?
Yes, I'm going to get to that. This is the transform plugin that was asked about. So this is just, it's a simple plugin that just does 8 operations that are geometric transformations, including the null operation where it doesn't do any transformation. And it's just the 8 possible combinations of a 90-degree rotations and a mirror symmetry. There are only 8. And the letter F here shows you what each of those choices does. So that's useful when your camera has to be mounted upside down, and you don't want the operator to be looking at an upside down image. Okay, so this is going to come to your question, Oksana. So there's now this PVA plugin that I described that lets you convert the ND arrays in area detector into these EPICS v4 normative type NT-ND array, and then serve those on the network. It's very efficient. This was written by Bruno Martins when he was here. So in this case, I'm showing 1024 by 1024 by float 32 images. So those are 4 megabytes each, and it's doing 784 frames a second. So this is like 3.2 gigabytes a second. So that's 3 10-gig lines, right? 10-gig Ethernet lines. And they can be received by any EPICS v4 client, Java, Python, C++. CSS has a widget. There's a new ImageJ plugin I'm going to show you today. And this comes to Oksana's question about can we farm these things out to multiple IOCs. You can include an NT-ND array receiver in another IOC, and that's going to be one of my next slides. Okay? So this thing takes an ND array, converts it into an NT-ND array, and puts it on the network. There's the inverse of this is a driver that listens for those NT-ND arrays, converts them back into ND arrays in another IOC. And so it's a way to put multiple IOCs on your system that are not. So you're running the plugins not just in one process, but potentially in multiple processes on the same machine or on multiple machines. So you can spread it out. This is the PV access driver that I just described. So this is the logical inverse of the plugin from the previous screen, receives these NT-ND arrays, converts them back to ND arrays. It's not quite as fast going this direction as going the other direction, but here I'm showing 1.2 gigabytes a second, which again is still faster than a 10 gig Ethernet link to spread this out. Okay, then there are the file plugins. And I think we should, let's finish this up and then take the break rather than breaking now. It's going longer than I thought, but we're getting there. So there's file plugins. They have right now 3 modes they can work, where you write each disk file is a single ND array, or you can capture N arrays into memory and then write it to disk either as multiple files or a single large file, or you can stream arrays to a single large disk file. And for file formats that support it, it doesn't just store the array data, but also the attributes. And I already told you about that. So the file formats that are currently supported are TIFF, supports any ND array data type, and stores ND attributes as ASCII user tags in the TIFF file. There's a JPEG plugin with compression control, NetCDF plugin. NetCDF is a popular self-describing binary format supported by these guys, University Corporation for Atmospheric Research in Boulder. The HDF5 plugin, I think most of you are probably familiar with HDF5. It supports actually more than 3 types of compression now, and it supports using an XML file, a different XML file than the one for the attributes, that describes the layout and placement of the attributes within the HDF5 file. So there's a default layout which is compliant with the Nexus format. Nexus is a standard way of laying out an HDF5 file that's been adopted by the neutron and X-ray scattering communities. The default layout, if you don't use one of these XML files, is Nexus compliant. And then this does support what's called single writer, multiple reader, or swimmer. And what that lets you do is, let's say you're writing a really big HDF5 file and you don't want to wait until you're done to display it. You can be writing it and have a client that's reading it at the same time. But there are some limitations of that. So you need to understand that before you use it. There's also a Nexus plugin that it writes the same kind of files as the HDF5 plugin, but it uses a different API, uses the Nexus API. This may be deprecated because it's really not necessary. Now that the HDF5 plugin can let you control the layout with an XML file, we really don't need this plugin. There's a Graphics Magic plugin that lets you save in a variety of different formats, JPEG and TIFF, just like we already have another plugin, but also PNG and PDF and Windows bitmap and a whole bunch of others. And then there's something called a null file plugin, which doesn't actually write any files, and I'm not going to get into that. There's one thing that is important to realize, though, is that many drivers, like the Pilatus driver we already talked about, the driver itself can save files. The vendor software can save files. So this area detector supports that. So you don't have to use the file plugins in area detector if you're happy with the file format that the vendor is providing. One of the limitations, though, is that the vendor software usually doesn't store metadata. It's not going to store the metadata that describes your experiment in most cases. But if the vendor format is what all of your analysis software is based on, and a lot of times it is, right? People know how to read MAR-CCD images, or they know how to read Pilatus TIFF files or CB4 CBF files. But they don't have the metadata. So what you could do is use the vendor library, but then you could make a thumbnail TIFF, bin it 16 by 16 so that it's a tiny little image, save a TIFF file with the area detector plugin, and put all the metadata in that. So you're not taking up much disk space, but you are saving the metadata. So this is just what the TIFF plugin, file plugin looks like. For all of them, you set the path, the file name, and a file number, control whether that file number is auto-incremented. You build a C format string There's always an example here to copy of that describes basically how it puts together this string and this number to build the final file name. But you can put additional characters in here, like in this case, the underscore was added. And then it tells you here what the final file name was. And this is where you select, do you have a single file, streaming, and so on. Even for TIFF, it doesn't support putting multiple images in a single TIFF file, but you can still use this stream mode, which on an HDF5 or NetCDF, that would put 1,000 images in a single file. With TIFF, it creates 1,000 TIFF files. But you can still specify, I want to only collect 1,000. So you can say 1,000 files, start, and then once 1,000 files have been collected, it'll stop saving the files. There's also something here called autosave that only works in the single mode, and that just means every time it gets a callback, it'll save the file. But you've got to be careful with that, because you forget to turn it off, and all of a sudden your file system is full. This is the HDF5 plugin. Same kind of stuff up on the top, but here you can set levels of compression for zlib or szip. This is an old screenshot. There's now BLOSC compression as well, which is another compression library that is supported. This is an example of one of those XML files that I was talking about that you use with the HDF5 plugin to control the layout. I think I'm going to skip this because I'm going to show it in the demo. But basically, you can run multiple, you can take a plugin and for many of them and run multiple threads and increase the throughput. So if a single statistics plugin can't calculate fast enough, you can run 3 of them, 3 threads within the same plugin and run it 3 times as fast. I'll demonstrate that. I'm going to skip the scatter. This is an example. There's something called a scatter and a gather plugin. I'm only going to mention the scatter. So normally, when a plugin gets, or when a driver plugin does callbacks, or the driver does callbacks, it calls every plugin that's been registered for callbacks with every frame. The scatter plugin doesn't send every frame to all the clients that have asked for it. It does it in a round robin. So it sends the first one to this plugin, the next one to this plugin, and the next one to this plugin, and then back, back, back. So it's a way of sort of fanning out the load to multiple plugins. And here's just an example of doing it. Somebody wanted to be able to write files, HDF5 files, faster than this library permitted. In other words, the file system was really fast. The bottleneck was the HDF5 library. It couldn't run at the full rate. So what we did is we took the SIM detector, ran to a scatter, ran 3 different PVA plugins that were feeding their output into 3 IOCs. Right? So there's now, these are 3, back to Oksana's question, these are 3 separate IOCs that are running that PVA driver. So they're all getting their data over the network, although in this case they were all on the same Linux box, so it wasn't really the network. And then each of those was running an HDF5 plugin. So if I only ran one IOC, I could only get 100 files a second, which was 1.2 gigabytes a second. But if I turned on all 3 of them, I could get 217 files a second, which was 2.5 gigabytes a second. So that's a use for this scatter plugin here. It wasn't, because at some point you're probably saturating the memory bandwidth of the computer. These were all writing to a RAM disk, so I don't think that the RAM disk was the limit. I think it was how fast this bandwidth required here.
So when they're running on the same server, they're running on different cores in the same thing? Is that?
Yeah, yeah. This is a 20-core machine.
So by starting a different plugin, doing it this round robin way, each one gets onto a different core. Otherwise, it would be on the same core.
Yeah, and really, it's the fact that the HDF5 library is not multi-threaded, right? So it's a bottleneck that the HDF5 library is only running in a single thread or a single core, but now I've managed to have 3 instances of the HDF5 library, each running in their own core. Yeah, any questions? Okay, finally, I'm just going to talk about viewers here. So there are, generic viewers. There's the ImageJ ones that I'm going to show you, both for channel access and PV access. There's an FFmpeg server and an FFmpeg viewer. Those are from Diamond. There's obviously CSS as well. So this is the EPICS PV access viewer. Essentially the same as the channel access one. I'm going to show you both, so I don't think we really need to go through this slide. And okay, but coming back to the question of why would you use PV access versus channel access? So this is the sort of summary of why I think it's a good idea to use PV access. First of all, the data is transmitted atomically over the network. When we use channel access, channel access is very limited. It only supports one-dimensional waveforms, one-dimensional arrays. So we've got to take our two-dimensional array or n-dimensional array, collapse it to a single dimension, and then there's other PVs that say what's really the x dimension, what's really the y dimension, and potentially the z dimension, what's the data type? Well, and when is there new data? So it's not an elegant way to do it, right? Because you need to guarantee that those PVs are all in sync with the actual data in the array. So it's not an elegant way to do it at all with channel access. So PV access just puts out a structure that is the data, and it contains all the attributes, it contains the dimensions, everything. With channel access, let's say you want to look at 8-bit images, 16-bit images, and 64-bit FFTs from the same IOC. Then your waveform record would need to be 64-bit for the widest thing you want to look at, but that would add a factor of 8 overhead when you're only viewing 8-bit images. PV access changes the data type of these NT-ND arrays dynamically. So first you're sending 8-bit data, and then you're sending 64-bit data. And there's no inefficiency, and nothing is fixed at IOC boot. Here the data type of your waveform record, if you want to change it, you got to reboot. You got to edit your startup script and reboot the IOC. Also, I think you've probably all struggled with EPICS CA max array bytes if you've played with Area Detector, and EPICS channel access by default, only has a 64 kilobyte buffer. And if you want to look at any array that's bigger than that, you have to set this environment variable both on the server, the IOC, and on the client. It's a pain in the neck. You don't have to do that with PV access. There's no limit on array sizes. I'm going to show you this EPICS AD controller. So it allows you to use the ImageJ, graphical tools to set regions of interest or set the readout region of your detector, or to set the position and size of an overlay. And finally, I already mentioned this, that Area Detector isn't just used for two-dimensional detectors. It's used for things like the Express 3 and the XMAP and the Falcon X from XIA. It's used for time series data from the quad electrometers like these. And finally, so I think it's an architecture that works well. A lot of these things are generic. They're not really area detector specific things. We use it for other kinds of detectors. And this is the home page for the documentation, and this is the home page for the source code that's on GitHub. All right, thanks. Any more questions?
Why would you want to use channel access instead of PV access?
Because there are a lot more clients that right now that know channel access than there are that know PV access. There are also some of the channel access client tools are, in my opinion, they're richer. Like even CA GET. If you want to do CA GET on area detector waveform record, you can say CA get minus pound 100 and just get the first 100 elements of the array, but there's no equivalent in PV get. So your screen gets overwhelmed by 4 megapixels, and you can't trim that. These are things that'll come with time with PV access. They'll add features, but right now there are some things that are a little easier to do in channel access.
Is channel access faster than TV access?
No. I mean, they both can saturate the network. Well, let me just say that I've got 2 plugins. One that the standard arrays plugin that converts to channel access waveform records, and the PV access one that exports the arrays. The PV access one is significantly faster. It's not that you get the data across the network faster, it puts a less CPU load on your IOC by like a factor of 7 we measured yesterday. Yeah. Yeah, but I've measured it. That the PV access PV access plugin in the IOC is significantly faster. And in ImageJ, I believe that the PV access viewer is maybe 1.5 times, 2 times faster than the channel access viewer. But I have less confidence in that number. Yeah. Question?
I have one question. You mentioned a couple of times about the spectroscopy systems, like Expo3, for example.
Yeah.
Do you know that many people are using the plugins for those types of systems?
Oh, for sure. Yeah, because, for instance, the data that comes across from the Express3 is an n-dimensional array where it's the number of channels, energy channels, times the number of detector elements, and there might even be the number of spectra in some block. So the region of interest stat, the ROI stat plugin, is used to separate out the individual spectra and display them. I mean, Matt Newville's doing that on the beamline at Sector 13 at the APS. We've with the quad electrometer, that data for sure goes into the time series plugin, because then to the FFT plugin, because with the quad electrometer, we're getting real-time FFTs of the spectral, where's the vibration on my beamline? What's the spectral characteristics of the beam intensity, spectral components. And then also with the Express3, they're streaming to HDF5.